Hello, I'm going to show you a new way to teach negative numbers to fifth graders. First, we start off on how we create our numbers. We start off with the number 1. The way we get to the number 2 is to add 1. The way we get to number 3 is to add 1. If we look at the number before 1, which we will call NB1, then NB1 plus 1 is how we get to 1. 2 would be defined as 1 plus 1, replacing that 1 by its equivalent, what we call the transitive process. We would get NB1 plus 1 plus 1. We reassociate these and we get NB1 plus 2. So this number before 1 has the property, when added to any number, it gives us that number back again. This is the identity property. And what we will call this is what you're familiar with is the number 0. If we look at the numbers before 0, let's call them A and B. To get from A to 0, we do A plus 1 is equal to 0. Therefore, A is equal to 0 minus 1, which we will call minus 1. Then B plus 1 is the way we get to A. But if we add 1 to both sides, we get B plus 2 is equal to A plus 1, and we know that A plus 1 is equal to 0. Therefore, B is equal to 0 minus 2 because of the way we define subtraction, which we will call minus 2. We now see how we have named our numbers on the left side of 0. Let us now erase this. And we had noticed that B plus 2 was equal to 0, and we had shown that B was equal to minus 2. Therefore, minus 2 plus 2 is equal to 0, and similarly with the A, minus 1 plus 1 is equal to 0. Therefore, we will generalize this by saying a number plus its negative is equal to 0. Using the definition of subtraction, when we move n to the other side, we get that negative n is equal to 0 minus n, which we had shown before. Interestingly, we also will get that n is equal to 0 minus, bringing the minus n over to the other side. Now, what we'd like to do is to show what the properties of adding and subtracting negative numbers and how we develop the rules. So we will start off with m plus 0 is equal to m. This is what we call the identity. Then, subtracting m from both sides, we call this subtraction. And then we will group this, which would be association. And we know from this over here that 0 minus n is equal to minus n. So we've now developed rule number 1, which says that when we add a negative number to a number, we get the answer by subtracting that number from the number. Now let us develop another rule. We will erase this to give ourselves some room and rewrite the basic rules. N plus minus n equal to 0, minus n equal to 0 minus n, and n is equal to 0 minus minus n. Now, let us do the same thing again, except this time, instead of subtracting n, we will subtract minus n from both sides. Again, using the associative process, this time we look over here and we see our 0 minus minus n is n. And so now we have a new rule. When we subtract a negative number from a number, it's the same as adding that number. So we now have rule number 2. So we have two rules, one for adding negative numbers and one for subtracting negative numbers. Let's write these rules up here. M plus minus n is equal to m minus minus n, rule number 1, and rule number 2, m minus minus n is equal to m plus n. We just interchange the sides of the equality sign. Now let us continue to prove some other rules. You'll notice the parallel that we had, that we were able to use the same logic for developing rule 1 as we did for rule 2. We now know that when we add a negative number to its positive equivalent, that we get 0. So we have 0 plus 0. We're now going to use the commutative property to get our negative numbers and our positive numbers together. So this will be the commutative property. This is the definition of a negative number. Then we associate these as we did before. And now we use the definition of subtraction to bring this over to the other side. But we now notice this follows the same thing, except we have a more complex expression, but this should then be replaced by minus m plus n, which basically says if we add two negative numbers, it's the same as adding these positive numbers and putting a minus sign in front of it. So we now have rule number 3. Minus m plus minus n is equal to minus m plus n. And now let's do the same thing again, except instead of exchanging the numbers next to each other, we'll exchange these two numbers. So we have m plus minus n plus n plus minus m equal to 0. Okay? And what we will do is we will associate these as we did before, but now we look at rule number 2, which says that, or actually rule number 1, which says this can be replaced by m minus n plus n minus m equals 0. So this is rule number 1. Okay, and now, using our subtraction definition, and in this case, we now discover, again using this rule over here for replacement, that when we're subtracting a number that's bigger than a number, we reverse the order of subtraction and put a minus sign in front of the answer. So this is rule number 4. So we now have discovered that we can actually prove these rules that we are normally told in the class on what the rules are for adding and subtracting negative numbers. The other thing that we should notice before we go on further is that the definition of negative numbers is rather arbitrary, because if we go to a clock and put our numbers on the clock, what we will discover is that the number before 1 is 12, which acts very much like the 0. When we add it to any number, we get that number. If we multiply a number times 12, we get 12 back again because we're just recycling on the clock. So even multiplication-wise, it acts like the 0. And if we look at the number before 12, the 11, that acts like minus 1, because if we add 4 to 11, we get 15, which turns out to be 3 o'clock on the clock. So even though this doesn't have a minus sign, it acts like a negative number in the same way. This is modular arithmetic, modulo 12. On computers, we use a very similar technique, and we find on computers that our numbers are not written with a minus sign in front of it. Okay, now, the beauty of this is we can now learn fractions very quickly by wherever we see a multiplication, a plus sign, we make it a multiplication. Wherever we see a minus sign, we make it a slash or a division. So let's go and prove some of these rules for fractions. Now the way we will define a fraction is that n times slash n is equal to 1. Wherever we saw a plus, we replace it with a multiplication sign. Wherever we saw a minus, we put a slash. Now, if we use the rule for division, this is equal to 1 divided by n, which we sometimes write in this form. So a fraction is really another form of division. We're not used to writing a fraction this way, but we'll find that in our replacement, it will make it easier for our proofs. So what we will now start off with is m times 1 is equal to m, the identity, in the same fashion as we did with fractions. This would have been a plus, this would have been a 0. Now we take, and instead of subtracting, we divide by n. I'll just put a slash there, equal m divided by n. And what we find in this particular case, that 1 divided by n is equal to slash n. So m times slash n is equal to m over n. So all this really tells us that when we see a fraction like 3/5, this can be 3 written as 3 times 1 over 5. You basically didn't have to take this step, but it was easier in our proof. So this now becomes a way of showing how we do our fractions. Now, let's take our m times 1 over n times m times n times 1 over n equal 1 times 1 equal 1. Definition of a fraction. And this time we will interchange these two. So we get m times n times slash m times slash n equal to 1. We'll now use our, and we get slash m times slash n is equal to 1 divided by m times n. And if we come up here and look at our definition, 1 divided by n is equal to slash n. So we have m times slash n equal to slash m plus n. But as we've seen from this definition over here, we can just rewrite these as 1 over m times 1 over n equal 1 over m plus n. So what we've discovered is that by using the parallel approach, a pattern, a template that we use for doing negative numbers, we can also do the same thing to find out about fractions. We have tried this method with top 5th graders in one of the local high schools, and we found that the children taking this felt their minds have been opened to a whole new world of understanding of mathematics. We've also tried this in inner city middle school, and we got exactly the same results. Thus, we feel that with this particular approach, we can greatly enhance how math is being taught now. Thank you.